Hi everyone and welcome to a new video. Today we'll see how to price a chooser option with the Heston model, and in particular we price one specific kind of choosing option that we'll see later on while writing the code. So first of all, as you see, I can import two needed libraries, so NumPy SMP and then the PyPlot library to do some plot, and but we'll see later on in the video. Okay, first of all, we need to set the Heston model parameters, and in particular, okay, first we have the stock prices, so the initial stock price which we set, for instance, 100. Then we have the stock price of the option, and we set it equal to a 0, so to have at the money option. Then the maturity, time to maturity, which is, for instance, 1 year. Then we have the risk-free rate, 5% is good. Then the starting volatility, which is, for instance, 4%. Okay, then we have theta, which is the long-term mean of volatility. So again, equal to V0, for instance, as 0.4. Then we have K, kappa, also called kappa, which is the mean reversion speed of volatility, 9, for instance. Then we have sigma, which is the vol of vol, the famous parameter volatility of volatility, for instance, 30%. And finally, rho, which is the correlation that we have between the stock price and the volatility, and usually it's set as minus 50%, so to have a negative correlation between the stock price and the volatility, and this is common practice. Then the second part is the chooser option parameters, and in particular we have the time of choice, so the time to choose between to price a call or a put. So we have for instance alpha here, so 0.5, or maybe we can also do 0.5 times t, but it's the same in this way. Then we set the option type equal to call. Okay, and then we have, since we will price and with Monte Carlo simulation of the Heston model, we will have the Monte Carlo simulation parameters. And okay, the number simulations, for instance, I set to a low value, so 1000, just to let the code be a lot faster with respect to, for instance, 1 million. And but of course, you remember that the higher the number simulation is, the better will be the evaluation of the price. Then we have the number of time steps from now up to maturity. So we set, for instance, 100 time steps. And finally, the time step size, which is simply the maturity over the number of time steps. And okay, now we go to the most important part of the tutorial, which is the Heston model simulation. So Heston model simulation. And okay, first we initialize a new matrices of 0, which is simply the stock price evolution. So we use the NumPy function zeros, and the dimensions are the number of simulations, which is the number of row, and then the number of time the intervals plus 1, which this one is as 0. So the first the first column, which we'll set this way, so S of column and 0. So the first column, every row is equal to S0, so the initial price, as you can see here, 100. And okay, then we have the very same thing, but with the volatility evolution. So we call it this matrix V, and in particular we have the very same initialization, but here instead of S0 we have V0, which is this parameter, so the starting volatility. And then we have to fill all the other values of the matrices. So for I in range of 1, because the 0 is already implemented, up to nt plus 1, and then we have z1 and z2, which are the random variables. So the first one is just a simple standard normal random variable. So from numpy again we have mp.random.standard normal, you can see here, of how many we want number of simulations, so nsim. Then we create n2, and we have row times z1, so times standard normal random variable, plus the square root of 1 minus row squared. This is a very famous formula of the Heston model, so if you don't know, if you're not familiar with that, we can also check on the web. It's many websites. And okay, 1 minus row squared over the square root, and times the random standard normal again of nsim, so standard normal of nsim. And remember, this must be difference, of course. I cannot say again times z1. Okay, then we implement and we fill all the other parts values of the matrices V and capital S. So V is simply the absolute value of V in I minus 1. I forgot this. Okay, V of I minus 1, so the previous column, plus the kappa parameter times theta minus again V. I just copy and paste this, so V of the previous column, so V of column and I minus 1, okay, times the time steps, plus sigma times the square root of again I minus 1, so mp square root of V the previous column times dt, and finally times z1. And finally we have to fill the S, the stock price evolution matrix, capital S, and here we have S of previous column times the exponential of, and this is the Heston model, so the exponential of R, the risk-free rate, minus a half times V of I minus 1 times dt plus the square root of V I minus 1, again as before, V I minus 1 times dt times z2. And here we are. And I hope there are no mistakes, because it's quite complicated formulas to write on Python. And here we pass to the chooser option price. So we create this simple code to price the chooser option. So as choice, we let it be an integer, so int of t choice over dt. Sorry, over dt. Okay, so in this way we say we cannot say we cannot keep 0.5, because we are considering a discretization of 100 time interval, and in this way we are saying go to the 50 time interval. And okay, so we have, if the option type is equal to cool, then the payoff of course will be the maximum of S choice S choice minus K minus the strike and 0, so the positive part. Otherwise we have the payoff is equal to the maximum between K, so the strike price, minus the stock price. And this is the put case. And okay, the if else is over. And then we have the option price will be the exponential of minus the risk-free rate times the delta t, so capital T minus T choice, and all of these times the mean of the payoff, of course, because it's a Monte Carlo simulation, so we have to compute the mean. And we also want to check the standard error of our simulation, and we have the exponential of the very same, so I can copy it and paste. This time times the standard deviation of the payoff over the square root of the number of simulations, so np dot square root of number of simulations. And okay, I can see a mistake here. Yes, okay, just a typo, I think. Okay. Okay, now we can visualize, so visualization of the simulation, of course. So visualization of the stock price simulation, and simply PLT, since we imported the method library pyplot as PLT. So PLT.figure, and the fixed size I usually keep 10.5 because it can fill the whole Jupyter page. Then we have plot of s.t, and then we have plt.show. And let's see, and here you see the stock price evolution in all of our 1,000 simulations scenarios. And finally, the only thing we wanna check is the option price. So we can print, for instance, chooser option price, and then comma, we have the option price. And the same for the standard error. We print chooser option, we delete it, so standard error. Okay, and here we put the standard error. And as you can see, with all our set parameters, both the Heston model and the chooser option parameters, we obtain finally this chooser option price according to this standard error. And that's it. This is the end of the tutorial. I hope it's been useful for you, and thank you for watching, and see you in the next tutorial. Thank you.